MIT में पढ़कर हम चलते हैं सक्सेस की ओर। MIT Group of Academic and Research Institutions, Aurangabad, Maharashtra, announces admission in engineering and management with 40 years in technical education, over 12,000 plus students, best placement cell in world-class companies, best infrastructure. Bead Bypass, Aurangabad. Call 0240-237-5375 or visit www.mit.asia.
Good morning to all. Dr. Ganesh Sable, on behalf of Maharashtra Institute of Technology, Aurangabad, would like to welcome you all to second day of International Technical Symposium on opportunities and challenges in Industry 4.0. Before starting the session, all are requested to follow the guidelines of Symposium. I will just go through the guidelines. All are requested to attend all the sessions. As you know that we are assessing the attendance through the GoToWebinar also, and we are also recording the attendance using Google Form, the link of which will be circulated during the session for 20 minutes using the Telegram group and in chat box of GoToWebinar. Based on the content of each session, a short quiz along with feedback form is shared with you at the end of each session. Performance in the quiz has to satisfy at least 40% marks. For asking the queries in each session, a Google form link will be shared during live session on Telegram group and chat box. You are requested to raise your questions through it. And now I extend warm welcome to our today's expert, Professor Luigi Triono. Professor Luigi, working as an associate professor at the Department of Business Science, Management and Innovation, University of Sannio in Benevento, Italy. Professor Luigi is an expert and doing research in the field of AI, data science and big data. He chairs the Italian Technical Committee of ISO-ISE for AI and big data. Professor Luigi is University Ambassador for Italy of NV India Deep Learning Institutes. He is coordinator of CISCL lab at University of Sannio with aim at involving students in research activities and experimenting the application of intelligent system in industrial environments. Sir, we are honored to have with us today. Today he will deliver an expert talk on neurons, the emergence from simplicity. So may I request Professor Luigi to address the participants. Over to you,
Thank
sir.
you. Thank you so much. Thank you for this invitation. I'm very glad to be with you, with Professor Sable, and with all participants to this interesting symposium today. Well, today I will make just a very quick and fast. Just let me take back the presentation. Okay. So what we will speak about today? Today we will speak about AI and how at the basis of modern AI, in particular neural networks that are the most successful tool that we have today for facing real world problems in artificial intelligence. There is a very simple unit, the neuron, and this unit, it is very simple. It is very powerful when put together with other units. So starting from nowadays, we get that AI is really the breakdown technology that we have in Industry 4.0, and this role will become more and more prominent in the following years. But the question is, how AI is so promising and why we can expect so much from modern neural networks. So what we can say, just looking at results, is just a wow effect. So we are really astonished about what are the results that we can obtain by modern technologies. And we reach these results by a research that started in the early 30s with the work made by McCulloch and Pitts, and still now is ongoing with many researchers and practitioners around the world. Here we can see the main of these paths, and today what we will do is to make the same path in order to understand why neurons are so powerful in building complex systems. To do that, we will make a time journey, and this time journey starts well in 150 million years ago. At that time, human beings will not appeared on this planet, and the dinosaurs were absolutely the masters of this world. And here we can see the Allosaurus in particular, that was a very, let's say, dominant in that period. And if we see to this animal, to the skeleton of this animal, we see that the part that is devoted to contain the brain, it was quite small. So although the Allosaurus was quite much larger, bigger than a man, it was really small in the cage to keep the brain inside the skeleton. And this is becomes even more clear if we see to T-Rex. T-Rex is another very known dinosaurs, and we see that the part that was devoted of the skull to keep the brain was really small. As you can see here on the red region, that was actually the brain of the T-Rex. Then at a given time appeared a new evolution on the animal life on this planet, and this was the mammals. Mammals became dominant, but why? Because they basically invested a lot of resources in building the most powerful tool that we know nowadays to understand the world, that is the mammal brain. And why it is so important? Because as we can see in this evolution path that is starting from the placentas, that is the common ancestor that we have among mammals, up to human, we can see that the brain became more and more complex, not only in terms of functions, but also in terms of morphology, because as we can see, the shape of the brain became more and more structured and specialized. And as you can see here, the region that is assigned to visual area, auditory, and somatosensory area became more and more smaller, reaching the human. And a large part of the human brain was left to cognition. And if we restrict our attention to monkeys, we see that this effect is even more important. And if we start from the mangabe that we can see on the top, and we reach the brain of the Homo sapiens that we can see below, we see that basically the area devoted to each part of the brain became larger and larger. So keeping more and more neurons. But it's not just a question of keeping neurons together, but it's also about the function and the architecture that we have for the brain. Indeed, if we see how the structure of the cortex change, moving from amphibians that we see on the left up to humans, what we can notice is not just an increasing number of neurons, but is an increasing number of layers. And as we can see, the layers can play a very, very important role. Why? Basically because the deeper layer that we have in our brain are the way to make connections between regions that are farthest in the topology of the brain. So this means that by keeping deeper layers, we are able to make stronger and deeper correlations between information that we keep by our human brain. Indeed, if we see what happens between the mouse and the macaco of in this image that appeared in a study from Nature, we see that basically this layer became, and the structure becomes deeper in the macaco with respect to the mouse. So there is a strange correlation, not only between the number of neurons, but mostly between the number of layers. So what we can learn from this deep in nature is that structure really matters. So let's move in the future, and we reach the 1933. At that time, there was a really pioneering study made by McCulloch and Pitts that produced the artificial neuron. At that moment, there was a lot of interest in mathematical logics and theoretical logics. And here we can see the basic operations that we can get with the two Boolean variables. At that moment, it was believed that in some way, the only way to map these functions to implement these functions was by a given true or table true, so that the output, corresponding output, was given for each combination of the inputs. That was, and this is still one way we teach logics actually. But the intuition of McCulloch and Pitt was very incredible, because they said, well, we can obtain exactly the same logic function, not by a dogmatic approach, but by a computational approach. And this can be done by a one single unit, the artificial neuron that we can see outlined here. So it's very simple one. We get a bunch of inputs. These inputs are weighted by corresponding connections, by coefficients can be +1 or -1, and then we have a corresponding threshold, and the meaning of this threshold will provide the semantics of this unit. So that if we would like to get the conjunction, we just need to give the two inputs to sum up the two inputs, and then to see if they are over, let's say, a given threshold of 1.5. If that is the case, we get 1 as output. Otherwise, we get 0. That is exactly the conjunction. Instead, if we decrease this threshold to 0.5, our function will work as our neuron will work as a disjunction. Indeed, just one high input will provide an high output. In the similar way, if we multiply by -1 the input, and we use -0.5 as threshold, we get a negation. And we could continue with many other functions. But the key point here is that we can already keep one of the complete functional sets that we know for the Boolean algebra, just with the same neural unit. So this means that we can replicate a complex circuit, logic circuit, just by connecting these units. So here we can see how the circuit that we see on the top can be easily replied by a neural structure that we can see below. And it's very, very simple to aggregate. So you can simply identify the disjunction, the conjunctions, and the negation that we can see on the top. So what we learn from this lesson is that connectivity matters. Another important milestone just arrived a few years later, in the 1957. At that time, Frank Rosenblatt made the generalization of the work of McCulloch-Britt, and he introduced the concept of perceptron. The perceptron is basically a generalization of what we saw before, because we can work with this unit not only with Boolean inputs, but for any numeric input.
Hello, sir.
And the logic is exactly the same. We make a scalar product between an input vector and the weight vector, and the result is compared against a threshold. And if the threshold is reached, we can fire an high level as output, or we get 0 as output, or the low level for the output. So what is the equation? The equation is this one. This is the equation that is providing the logic of the neuron. And it's very, very incredible simple. What do we get by this equation when we consider only two inputs? Is this linear equation that we that will simply lead to a line, and this line will be placed on the input space in order to split points of our interest, so that we can make a discrimination between the set 1 and set 2 that are outlined in this picture. And if we move this, if we change the parameters of this line, the line will move over the Cartesian plane, so that the quality of distinction between the two sets will be given by choosing the proper weights, in a very similar way on what we saw for the logical space. So, as we know, given a line, we have two versos that are orthogonal and that can provide the meaning of the two semiplanes, so that we can assign the positive semiplane or the negative semiplane according to this vector. And if we move the bias to 0, this line will pass by the origin, and as we can see, the bias actually plays the relevant role of placing the line properly on the plane. So what we learn here is that connectivity, again, is an important issue. So we move forward, we reach the 1960, because up to now, let's say, we understood that neural units are quite flexible and reusable unit. They can be used to address logical problem, but at the same time, they can also be used to represent the input space. But still, we don't have any clue about how to choose the parameters of such unit. We have to wait the work of Widrow and Tedoff in order to get the first learning algorithm. that is basically performing an adjustment of weights in order to move properly the line on the plane and to place in a proper position, able to minimize the error that network is performing. So in this period, from this moment, the neural network is not just a functional unit, but becomes also a trainable unit that is really making a difference with respect to other technologies, where the logic is by design, here is by training. So in this case, we learn that the unit can learn actually from data how to work. We move still forward, and we reach the 1970. At that moment, there was a really we have to understand what the 70s means in order to fully understand that moment in AI. So in the 70s, we have that the logic performed by symbolic reasoning was much more wider and stronger than the studies in neural networks. And one of the major exponent of this line of thinking was Marvin Minsky. And he was so influential that when he published this paper, this book, Perceptrons, we got that basically a new problem to face that really challenged the research at that time. The problem is known as the XOR problem, or if you want, the equivalence problem. In this case, we know that the XOR is not linearly separable. So basically, by one single neuron, we can replicate all the logical function except the XOR function. And now we know that this problem is only partial, because to solve this problem, we can put together two layers of linear neurons. And this is also leading us to understand that keeping layers in artificial neurons is so much important, similar to what happens in nature. And so nowadays, let's say this is a really trivial problem that is not so fascinating anymore. But it's still opening to another problem that we have in research now that is known as anti-learning. In anti-learning, what we get is that once we learn a relationship between data, there might be one single point that will challenge the whole learning procedure. If we consider again the XOR problem that we see outlined here, we can simply understand that if I remove just one of these dots, the problem will not be learned in any way. And I can still use one single neuron to solve the problem, because if I remove one green dot or even one red dot from this data set, the network will be, let's say, the neuron will be able to work perfectly with 100% of accuracy. But once this missing point appears, come to the scene, suddenly the neural network will not work at all. So this is a very challenging problem that we have now. What happens to our architectures when we have a novelty in data that will largely affect the way the network is working? So let's move on in time, and we reach the 1986. This is really another important date, because in this year appeared the work of Ramellart, Hinton, and Williams about the backpropagation. That is a generalization of the learning rule that was proposed in the past, and it's a very elegant and still so effective way to teach, to train a neural network. Think about that any other learning algorithm that we have now, up to the algorithm that we are using for deep learning, for example, Adam or any other algorithm that is employed for learning, for training deep neural networks, are still based on the stochastic gradient descent algorithm that is at the base of the backpropagation. And what we get from this moment is that we have an effective way to train neural feed-forward neural architectures that are made by several layers. And so this is a very important date in history, because from this moment we can start to fully exploit the potential of connected layers in order to train more and more complex architectures. And what we see is basically the following. Coming back to the sort problem that we saw before, we can simply put two different neurons, for example. We could or even consider 3 neurons or even more neurons, but we just need, for the moment, 2 neurons. Why? Because each neuron at the first layer will be able to define a line in order to isolate one point from the others. So this means that starting from this space, we move to another space that we see here on the figure B, where actually the only combinations that we can get are P2, P1, and P3, P4. So this means that for any combination of X1, X2 that we observe to the input of this network, we can only have 3 points as input to the last neuron, that is the third neuron. And there we can put another line in order to split and solve the problem. So this is also teaching us an important property. We first need to move from the input space to a perceptual space that is basically the starting point from logic. And from that moment forward, we can move in terms of logic. In order to understand the importance of this statement, think about that our brain is able to process logical information starting from perceptual information. So in some way, we are on the path of replicating the same functions that we have in our brain. We move forward again and we reach another important years. Here we have 2 important years, the 95 and the 1996. In the 1995 appeared the pioneering work of Vapnik and Cortez about the vector support machine, the SVM. What is the idea that is behind their method? That is, whatever is the input space, we can imagine to use a linear separation, even when these points are not linearly separable. And this can be done in terms of a kernel. A kernel is basically a nonlinear function able to project in a higher dimensional space our input space, so that in that space we can get a linear separation of our initial points. To understand a simple kernel, let's start with a polynomial classifier. So if we consider this equation is a quadratic equation that is not, so it's not anymore a line. Here we see many instances of that equation for different combination of parameters. And if you think in a geometrical way, this means that we are able to make any equation, quadratic equation, is basically a section that we get from a plane intersecting this biconic structure. So any equation is there. This means that if we start from our points, we are able to plot these points in a higher dimensional space, and there we can perform just a linear separation of points. Okay, here you see other possible combination even for lines and points. In other terms, this means that if we replace our original variables x with a new set of variables z, in this case, the equation becomes linear. So, in other terms, what we learn from this moment is that if we are able to perform a nonlinear mapping in a higher dimensional space, there we can work easier and better with neurons in order to make our decisions and to start with logic. So the mapping in a higher dimensional space is very, very important. For example, let's consider this structure. How we can split the red points from the green points? It looks like a very hard problem. Well, actually, if you just give a punch in the middle of the paper, keeping these points, what you get is exactly what geometrically we can see here. So that the red points will reach a level that can be easily separated by green points. So in some way, what we need is an higher dimensional space where to embed the observational data, and in that space we can destroy the original structure and we can reconstruct then the logical structure that will be able to solve our problem. And in the spirit of the same line, even completely in an independent way, and let's say also following a completely different ideas, just nowadays we are able to put the Vapnik idea with the LeCun idea of convolutional neural networks together. The idea of LeCun was basically to perform a local search of patterns to make to project them in several layers of features maps, and then to combine later with the fully connected layers. So coming back to the approach that we are following so far, we can say that the perceptual space is what is mapping from the input up to the last convolutional up to the layer S4. And from that moment, we move to a logical space using connected layers. So if we would like make a parallelism with biology, we could say that logic is deeper in the layers of our neural networks. So the deeper layers are those that are responsible for logical function. So just providing a really quick overview of convolution, we know that the convolution is basically the multiplication of a pattern for a kernel, and that is rotated by 100 degrees. And according to this equation, we get that if there is a match between a given pattern provided by the red dots and the input data that is given by the green square, we can get that moving the kernel across our image, we can recognize where that patterns will appear. For example, when we reach the grade of 9, we have the perfect match. How we can make this convolution, that is a very complex mathematical object that has been widely used in many fields, starting from telecommunication, for example, with a neuron again. It's quite simple, because if we linearize the input the input tensor for our neuron, what we get is that the weights of our neuron will be exactly the pattern we are searching for. And as you can see, given different inputs, we get a different score. So a neuron is able to perform a single search for a pattern. But if we place several neurons in parallel, this operation that is sequential can be performed in a parallel way. The basic idea is to keep a local receptive field that is sharing the weight with other fields, as you can see, but related to a different portion of the input. So using many layers, many neurons together, we are able to recognize at one time where that pattern is found. So we can get the forward, we get the backward for the training, and finally we can put several layers in order to search different patterns at the same time. And this is exactly how convolutional neural networks are working. So we move forward in time again, and we reach the 2010, 15 years later. In that year, the term deep learning was provided by Jeffrey Hinton, that with Joshua Bengio and LeCun are the winner of Turing Prize 2 years ago, and they are at the moment the most influential researcher in the field of neural networks. So I would like to share with you this image, a universe made of stars, because actually that is how our data appear in the observational space. To make understand this picture, think about an image made of pixels. We know that if we would like to portray a face, for example, we cannot get any combination of pixels. We need that pixels will be placed in a proper space. So this means that for example, if we consider an image made by 256 by 256 pixels, we get an input space made by an observational space made of by more than 65,536 dimensions. It is a huge space in terms of dimensions, but this space is very sparse because only few dots, a very minimal part of these dots, data points, will reflect a proper face. There is a lot of no-sense possible images between two meaningful pictures. So in the same way, we get a lot of space between two stars in the universe. But what is the internal structure of this? Because there is in some way an internal structure that is distinguishing, for example, a face from a ball or from simple noise in our images. There must be something connected. Well, this is a very important concept that we have in neural networks that has been exploited, but let's say not so much as it should be. That is the manifold hypothesis. The idea is that our observational data are expression of a nonlinear space where the nature that is much lower in dimensionality, where these points rely. In order to understand this concept, let's consider, for example, the expression of phase. The expression of phase is made of several independent dimensions that could relate to the position or to the expression that we have on face. If we are smiling, we are not smiling, if you are surprised or whatever. And so the number of dimensions that can produce a face is much smaller than the space where that image is captured. And this is exactly the manifold. The manifold, just to remember, is a geometric entity that is locally linear. Indeed, if I move my face just slowly, you can see that you can get the position by linear interpolation between the starting point and the arrival point. If I move dramatically my face, this is not anymore the case because the transformation is not anymore linear. But for small movements, this surface is linear. And so this means that if we are able to isolate the internal structure of our data, the minimal independent components that are representing our data, we are able to reduce the complexity of the problem. And this is basically where neural network can really work effectively. This is an example of what we are speaking before. Imagine to have satellite images, in this case airplanes, and the airplane should consider the position of lights, the shadows, and even the rotation of the plane on the ground. And if we are able to tangle together all these dimensions in a linear by linear transformation, we are able to understand what is the internal minimal structure of our data. So, coming back to our big picture, what we get is that we have an input, we get some non-linear function that can be performed by a neural network in order to project our input in an higher dimensional space where all dimensions are, let's say, broken. The initial structure is completely split in small pieces. And then these small pieces are recombined together in another space that is invariant, where the manifold structure is appearing. This is what we can see here is exactly this meaning. So we have several examples of 3 of 8s. We cannot make a recognition of 3 of 8s if we are not performing exactly this kind of mapping that we saw before. so that at the end, what we get is that whatever is the 3 or the 8, we are able to separate and split properly, even by a linear unit as the perceptron that we saw before. So again, by some neurons, we can easily split the region of 3s from the 8s. And the other important concept that we got is that in a neural network, we have several modules that we can put together in a similar way we do for coding, where functional units are placed together, but this time the parameters of these functional units can be learned by data. And the generalization of backpropagation to any kind of structure can perform exactly this kind of work. So, briefly speaking, the architecture of neural network is not so important as we think. We just need to put together some modules. For sure, we need to understand what is the meaning of each module, what is the purpose of each module, and then we can let the backpropagation to identify the best set of parameters in order to make all these building blocks working together. This is another important result that will be presented to ICPR this year. It's a research made by Google that is, in my opinion, is not surprising at all, because it was something that we were expecting. Is that if we increase the number of neurons, not the number of layers, but number of neurons, even to consider an infinitely wide network, so an infinite number of neurons composing a layer, what we get is that the probability of getting an output becomes Gaussian. And this is very important in order to make the problem convex. So this means that if we start to increase the number of neurons, the problem is easier to be solved. And this is not surprising in my opinion, because if each neuron is a line, it means that we are splitting by more and more lines our space, input space. On there, with smaller pieces of information, we can recombine in order to get the desired output. So I think this is a very important result, and that will be presented shortly to ICPR this year. And I suggest you to give a look to this work. So our journey is just finished. We come back to today, and these are the key points that I would like to share with you before concluding my talk. The first point is that we can get inspired by nature, because nature must be, because of needs to make things simple and to build a complexity from simple things. So a neuron is a very simple cell in some way, from a functional point of view, not from a biological point of view, but from a functional point of view is a very simple unit. And nature was able to exploit the aggregation of simple units in a more and more complex structure led by evolution, in order to make the brain, the human brain, one of the most powerful logical structure that we have in nature. The second point is that logic is not far from neural networks. They are very tied together. Indeed, we saw that all the logic can be implemented using single processing units that are the neurons. So we can make a connection between some years ago, in the 70s, symbolic reasoning was very, very popular. Then Minsky in the 90s, just before retiring, recognized that the work made by symbolic reasoning was wrong, and the correct direction was given by the work done in neural networks. But let me tell you that this is not the end of the history, because neural networks are still not able to process logical information. And in some way, I hope that similar to what happens in nature, even in the evolution, artificial evolution of networks that we are studying and designing, we will get a point where logic and perception will be again, they will work again together. Another lesson that I would like to share with you is nonlinearity. Nonlinearity, in my opinion, is something that is really overestimated. And if we look from the beginning of the concept up to the recent, the last work from Google, we see that the linearity is much more important than nonlinearity. Let me express you better this concept. I mean that linearity in a very high dimensional space is much more important than studying nonlinearity in smaller spaces. So, and it's much more convenient because we can just enlarge our embedding space, and we can work there much easier than in the original space. This is exactly in the spirit of haptic work. In order to perform this kind of mapping, connectivity is the key. We need to make as much as possible connections between units. And the other point is that we should make this in order to break the original structure in much smaller pieces of information, and then to let the logical space in order to recombine this original structure. So first break the structure of your data, and then let the logic to recompose them in the spirit of the problem you would like to solve. Locality is an intuitive means to decompose the problem. So we are now really good at making modules that we look at specific issues in data, and to build a hierarchy of correlation between data, so that at the end, modern neural networks are basically made of trainable modules. The architecture is not that much important, so you can design even your own neural network with all modules that you would like, but for sure, these modules should keep a logic role in your architecture. They cannot be just put together and see if something will work, because it's highly probable that it will not work just in that way. You need to keep what is the logic behind your architecture, and then to let the training algorithm to make the work for you. And now we are still at the beginning, but we have an initial understanding why deep learning is so effective in solving complex problems. And the work done by Google, but even by Benjo and other researchers in the world, are really breaking this this understanding of. That was the end of my talk. So thank you so much for your attention, and please feel free to post your questions. And you can reach me on LinkedIn if you'd like to get in touch with me. Thank you so much.
Thank you, sir. We will take some questions from the participants. One question from Dr. Arvind Chell is from Jawaharlal Nehru Engineering College, Aurangabad. The question is how we can decide the weightage average for input.
Excuse me, can you repeat the question, please?
How we can decide weightage average for input. in neural networks we find the weighted average.
Yes, the weights, how to choose the weights. The weights are given by the training procedure. So that is the most powerful idea behind the neural networks, that the structure can be fixed, the architecture can be fixed, but the parameters can be trained. And we can use a large data set in order to find the best match with, let's say, the best option for our weights.
So the second question is from Dr. Nidhi Sharma. She is from All India Shivaji Memorial, Pune. How the opportunities can be availed in the present condition in deep learning and machine learning?
What is sorry?
How the opportunities can be availed in the present condition for deep learning and machine learning? What are the different opportunities in the present scenario?
Well, first of all, deep learning is a branch of machine learning that became very popular nowadays because it's able to face real-world problems. And exactly because deep learning is able to face real-scale problem, complex problem, it became very, very popular. Where can it be used? Well, it is already used in many applications. Most of them that they are related to the perception field, so computer vision or speech understanding, text to speech, machine translation are all examples of successful applications that are already in place. For example, just a few years ago, if I would like to dictate a command to a computer, or I would just to make a long training session in order to recognize my voice and to understand the words. It was, let's say, a setup procedure that was really necessary for speech-to-text application at that time. Nowadays, you just go on Amazon, you buy an Alexa device, you plug in your outlet, and then it works. You don't need any more the training. Let's say the configuration time. You just need to provide a connection to the internet and it works. How is that possible? Basically because we are using neural networks. Up to 5 years ago, 5-6 years ago, Google Translator was really working. Let's say it was fascinating for that time, but not compared to human level. Nowadays, we have Google and even other translators that are really challenging human translations. So we can still this is another example. In the future, we expect that deep learning will be able to automate many cognitive processes where the human judgment nowadays is still relevant. I think about domains like finance, but also about business intelligence and many other business activities can be automated and humans can be assisted or even replaced in these fields.
Another question is from Surya Tiwari. We want to understand that how neural network used with a cyber twin.
How neural networks are used with cyber
twin?
Cyber twin. I'm not an expert about cyber twins, but digital twins. We should actually speak about digital twins. Digital twins are a replication of physical world. So in some way is one step in order to enable any automatic processing that we need to combine the physical world with digital world. So in some way, they will become a very important source of information for neural networks, and the output of neural networks can affect the digital model and then replicate it in the physical world.
We will take a last question, sir. That how we can explore the research activity with your universities? Can you suggest
how we can explore,
how we can explore the research activity with your affiliated university, with your universities? Can we explore some research activity?
For sure, we are Aurangabad. I was there, I think 3 years ago. I got a very good impression of your university and your region. I saw many young people very interested and willing to understand and to work in this field. So I think that considering the programs that we can try to explore, for sure there are possibilities to collaborate between our universities. More than universities are made by people, so it's very important to find a topic of common interest that we can develop together. So if there is anybody that would like to develop some research together, please, I would be very glad to explore if there is a possibility to develop some research together.
Thank you. So I would like to thanks to Professor Luigi for his highly informative talk on journey of neural networks and deep learning. I'm sure talk will certainly help the researchers in big way to carry out their research in these upcoming areas. It will also help industry persons to understand this basic of neural networks and challenges and opportunities in this area. I also thank all participants for active participation. A link for feedback and quiz will be sent to you all on Telegram group. All are requested to complete the same till 6 p.m. today. Next session will start at 2 p.m. All are requested to join till 1:45. And once again, thanks to Professor Luigi for sharing their valuable time, and in a short span of a time, they have accepted our invitation for this technical symposium. Thank you. Thank you very much, sir.
Thank you, Professor Sable. I was very glad to participate, and thank you to all participants. Thank you so much.
MIT में पढ़कर हम चलते हैं सक्सेस की ओर। MIT Group of Academic and Research Institutions, Aurangabad, Maharashtra, announces admission in engineering and management with 40 years in technical education, over 12,000 plus students, best placement cell in world-class companies, best infrastructure. Bead Bypass, Aurangabad. Call 0240-237-5375 or visit www.mit.asia.